fits best here. So we're going to be talking about indeterminate forms and L'Hopital's rule today. So kind of the objective of today is to kind of understand what an indeterminate form is, what L'Hopital's rule is, and how it allows us to kind of deal with some of these indeterminate forms. And so in the past, we have done limits, and some of the limits we've had, have looked sort of like this. Or, another common thing is limits that involved having an infinity in there, and we're like, what do we do with it? I mean, these are kind of like very conceptual things, I suppose. And they're certainly not just like easily understood, like, oh, duh, of course it's this or it's that. That's why these are called indeterminate forms, simply because anything divided by 0 is like, okay, this doesn't exist, but then 0 divided by anything is supposed to be 0, right? And so indeterminate simply means we don't really know what the answer is yet. The answer might not exist, or it might actually exist. It might be something. L'Hopital's rule basically enables us to do this, and we'll look at a little proof of L'Hopital's rule and how to use it. There are a lot of indeterminate forms that will get us to this place. The two that we are going to focus on are right here. So the basic idea is, if we try to apply a limit to an expression and we get infinity over infinity as a result, or we get 0 over 0 as a result, then those are the conditions that need to be met for us to use L'Hopital's rule. Let me jump down here real quick. If we got something like this, like 1 over 0 or 0 over infinity, I'm sure you can see how those sort of look like 0 over 0 or infinity over infinity, but importantly, they are not. Okay, those are not indeterminate forms that allow us to use L'Hopital's rule. Those are not, the conditions have not been met for L'Hopital's rule. So you've got to have one of these two forms in order for L'Hopital's rule's conditions to be met. And so we're going to be kind of focusing on those. As you can see, there are others, like this can lead back to one of those, this can, and then this one, if we have time, let's say on Monday or Tuesday, we might look at this because the tendency is to look at that 1 to the infinity and say, no, that is not indeterminate. That would actually end up being 1, right? That's the temptation to say that. I would just encourage you to think about it like this. If you said, hey, 1 to the infinity is essentially 1 times 1 times 1 times 1 times 1, so on and so forth. If you ever stop and say, and the answer is 1, didn't you just stop multiplying by 1? Hence, you have violated the to the infinity part, right? Doesn't infinity just mean you're going to keep multiplying by 1 in perpetuity, like forever? And for you to just stop, well, you didn't actually do it. You didn't actually do what it said. So, like I said, if we have time on Tuesday, if I kind of look at you guys and I'm like, hey, we've done like 2 or 3 examples. Do you guys have any further questions? And you're all like, maybe we'll just do this. Maybe we'll look at this. It's kind of outside the scope of what we need. So it's not something we have to do, but it is kind of a curiously entertaining thing.
Is that the thing where we do 1 to the infinity is e?
Potentially, yes. But I don't think we just do that. We would have to prove that.
Well, yeah.
Yeah, we definitely have to prove that. Okay, again, big takeaways here. I want you guys to understand the indeterminate forms that we will focus on in our course are these two right here, 0 over 0, or infinity over infinity. Those are the ones that we're going to be looking out for. Those are really the primary ones for L'Hopital's rule. So those are the indeterminate forms we're going to deal with, and then L'Hopital's rule allows us to deal with those. So let's see what L'Hopital's rule actually is. Let's look at a proof here to go along with this. So this is L'Hopital's rule right here. So if you are looking at some limit like this, and that limit leads you directly to, or indirectly to perhaps, 0 over 0, or infinity over infinity, then what you can do is you can apply the exact same limit, the limit in this case is x goes to c, of the derivative of f over the derivative of g. So I have a little note down there that says this is not the quotient rule, right? And it's tempting to think of it like that because it is a fraction, but we're not differentiating the whole expression that you're taking the limit of. We are just differentiating the numerator, and we are differentiating the denominator, and then we're trying to reapply the limit, okay? The truth is, as long as we keep getting these indeterminate forms, like 0 over 0 or infinity over infinity, you can keep applying L'Hopital's rule 2 or 3 or 4, or however many times, don't think we're going to go like half dozen times or anything like that. Just from a time perspective, it doesn't make sense. But a couple of times for sure. It's very realistic that L'Hopital's rule could possibly be applied. Okay, so from this perspective, L'Hopital's rule is not that complicated, is it? So if you get 0 over 0 or infinity, you just differentiate the top, differentiate the bottom, and then retry the limit. Like the mechanics of it are really quite simple. The notation can be a little bit, precise, right? It needs to be pretty precise, and we'll look at a couple of things that we'll want to be careful of. But let's take a look at a really brief proof here. Let me give myself just a little bit more room, and then we'll try some examples with L'Hopital's rule. And by the way, L'Hopital's rule, according to my old math history class, as you guys might guess, L'Hopital was a guy, right? Mathematician. And so supposedly L'Hopital is not really the one that came up with this. Supposedly L'Hopital was a particularly good student of one of the many Bernoullis. If you've taken physics or math courses, you maybe have heard of this Bernoulli family. It was a Swiss family with many good mathematicians and scientists and such. And so supposedly one of L'Hopital's teachers was one of these Bernoulli guys, and they came up with this, and he sort of like as that Bernoulli died, I guess, he like sort of took it on as his own, and he named it for himself. Or it got named for him, and he accepted it. So whatever. It's kind of how it worked in the day. Sometimes communication was not the best. We didn't have the publishing or the internet that we have now, and so things could get perhaps confused. Okay, so here we go. Check it out. So, if you start off with some question like this, limit as x goes to a of f of x over g of x, and you try to apply the limit, and as you apply the limit, you end up with this, or perhaps this. This means that the conditions for L'Hopital's rule have been met, and you can try to proceed with L'Hopital's rule, and here would be a possible proof of this. I would call this the baby proof. The big proof would be something you'd have to know something about what's called the extended mean value theorem. And the extended mean value theorem is probably a little bit beyond us. If you take an analysis course later on, you'd certainly work with that. But for now, we're going to just do this baby proof. So this baby proof kind of hinges on what I just wrote in red. F of a and g of a have to equal 0. Okay? So if that's true, then here's what I could do. I could say limit as x goes to a of f of x minus f of a over g of x minus g of a. And that's simply okay to write if I have the stipulation that f of a and g of a have to both be 0. If they were anything other than 0, you can't write that. Like, that's not equivalent. Okay, we got a fraction in there, of course. Isn't it totally okay with a fraction to do something to the top as long as you do the exact same thing to the denominator? So that's what I'm going to do next. I'm going to say the limit as x goes to a, and it's going to be f of x minus f of a. What I'm going to do to the top is I'm going to divide it by x minus a. And what I'm going to do to the denominator is the exact same thing. G of x minus g of a over x minus a. And I'm still going to do the limit as x goes to a of that. So again, all I've done is I've subtracted 0 from numerator and denominator, so not really much substance there other than form. And then I've divided top and bottom by the same thing. Still doing okay? A couple more steps. So the next step is to recognize that if you're doing the limit of a quotient, you can do the quotient of two limits. In other words, that limit would apply to the numerator and the limit would apply to the denominator. So it could maybe look something like this. Limit as x goes to a of the numerator over the limit as x goes to a of the denominator. believe it or not, as messy as we've made this look, I mean, you got to admit, basically in every stage we've made it look more and more complicated, right? But we're actually going to be able to wrap this up in one more step, depending on your recognition skills. What do you see in the numerator? I'll just put a box around it. Say again?
The derivative of x.
Yeah, it's derivative of f evaluated at a. And do you see the same sort of thing in the denominator? It's the definition of the derivative again, except it's for g. So what I can then say is, since the numerator is simply the definition of the derivative of f at a, the numerator is equal to f prime of a. And the denominator, for similar reasoning, would be g prime of a. So then if you look all the way back to what we started with this, and I think through acceptable methods, we have arrived at that, L'Hopital's rule. That makes sense? So this basically shows us how we can apply L'Hopital's rule once. If we wanted to talk about how you could apply it like a second or a third time, that's where you'd have to get into that extended mean value theorem proof of this. I don't know that I want to go there. So for the moment, we'll stop right there. Do you see the connection? Do you see how we've, obviously in somewhat of a circuitous path, gotten to where we needed to go? Yes, ma'am?
Why did you get rid of the limit as x, which is a?
Never did. I evaluated it. Are you talking about, like, why did this disappear?
Yeah.
So what I did is I actually did the limit. Oh, you're talking about right there? Well, so if you think about it, wouldn't you just do direct substitution here?
Oh, yeah, that makes sense.
Does that make
I
sense?
was just wondering why I was here. Okay.
Gotcha. Yeah, I get it now. Yeah, that makes sense. So x versus c, x versus a.
Yeah.
Okay. 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 So let's see if we can practice this a little bit. And I want to get into some notational things with you. So take a look at your first example. This first example, yes. Okay. Hey, I love thinking about this in the context of you guys taking a quiz or a test. If you were taking a quiz or a test, as you know, we've talked about this several times, it's not likely that on a quiz or a test you're going to see number one, and it's going to say the following is a L'Hopital's rule question, right? It's just going to be try this, try that, right? The question right after this might be a related rates. The question right before it might be some differential equation or a continuity question, and then this shows up, right? So what would you do with this? You remember way back, listen, do you remember way back in, gosh, it had to have been August, we talked about limits, and I said perhaps the easiest and most beneficial way to evaluate a limit is direct substitution, right? So you should always think about that. You should always think, hey, does direct substitution work? So if you do think about that, that's going to lead you to a very good place here, because if I think about direct substitution, I plug a 0 in for x, and I get 0 for the numerator. And I get, sine of 0, which is just 0, times 1. I get 0 for the denominator too, don't I? And so if you did do direct substitution, you would end up with 0 over 0. And in first semester, we would have been like, what could we do? Could we factor something out and cancel? I mean, what could we do to make this work? The question like this, the answer would have been like, there's no analytical way that we've learned so far to make this work. Maybe we could have turned to a calculator or a table or something and maybe seen something. But at this point, we would have kind of had to quit as the analytical part. Now, when we see this, 0 over 0, what would we say? L'Hopital's rule condition has been met, right? We try to limit, we got 0 over 0. And again, if I got 5 over 0, not a L'Hopital's condition. Infinity over 7, not a L'Hopital's condition, right? It's got to be 0 over 0 or infinity over infinity. So I want to be really careful here with notation for you guys. So check this out. I really hope you're all paying attention. I actually graded a question last year on the AP test that had L'Hopital's rule in it. And if a student did this, are you watching? If a student did this, I think it was worth 2 points, the question was. Maybe it was worth 3. I don't remember. But if they did what I'm about to do, they definitely did not get full credit. They lost at least a point. Okay? And that, now listen, that might seem arbitrary or particularly mean or something, but here's the deal. We're going to do L'Hopital's rule in a second, and we're going to find out that that limit actually is not equal to 0 over 0. It's equal to something else. And so sometimes we look at this symbol right here, the red parallel lines, and we just think the wrong thing. We think, oh, equals means and my next step is, or I did some stuff and I got that. And a lot of times that's kind of what it appears to mean. Here's the problem. We're saying that that limit equals 0 over 0, and later on we're going to say that same limit equals something else. You have really, honestly, violated what the equal sign means, and they tend to get pretty upset about that. Okay? So if you ever get this 0 over 0 thing, here would be my advice to you. Instead of writing equals, or if you do write equals, there's a way around this, I would just draw a little arrow. Now, little arrow is definitely indicating, and my next step was, or I did some work and I got this, but it's not equating two things, right? It's just saying I did some stuff and here's some important aspects of it, and my next step was this, blah, blah, blah. Yeah?
Would it be wrong to write like f of x equals x, and then f of a 0, and then g of x equals sine x plus 1, and then g of
Isn't it like a million times easier just to do an arrow?
Yeah, but arrows are for losers.
That was a pretty pejorative thing to say.
But would it be wrong to write that?
Say it again.
Just like f of x equals x, f of a equals 0, and then g of x.
What's A?
Or when, like, or f of 0 equals 0.
Got to be careful. I would say no. Peyton is not a fan of arrows, clearly. So check it out. What I just showed you definitely will be okay. Here would be the more rigorous way. If you're wanting the less loserish way and the more rigorous way, here's what you could do. You could do this. You could say the limit as x approaches 0 of x is 0. And the limit as x approaches 0 of sine of x times x plus 1 is also equal to 0. And that would also meet the conditions of L'Hopital's rule. So if you wanted to avoid the arrow, you could definitely do that. But so what you want to be careful of is saying f of 0 equals 0, because now you're equating a limit directly with simply an evaluation, and they're not the exact same thing. That makes sense?
Yeah.
So I could go either way. Either way is totally fine by me. Can I show you what you could do? Hey, listen. What if you, guys, should be a helpful thing for you. What if you're doing a question like this and you're like, okay, you just maybe out of habit write equals, and then you put 0 and, oh my gosh, 0, and then you're like, oh man, I put equals. Ugh. You know what you can do? You just turn the equal sign into an arrow. You can just go, I'm okay with that. I really am, because it is a little bit of a funky arrow, but style points, whatever.
That's not a loser arrow right there.
It's a fancy arrow, yes.
Classy.
Definitely fancy. Okay, so the idea here is this means that L'Hopital conditions have been met. You guys with me? So you draw the arrow, or you do the more expanded version, limit of the numerator, limit of the denominator. You basically prove that L'Hopital's conditions have been met. And once L'Hopital's conditions have been met, you can proceed forward with L'Hopital's rule. So I'm sure you can imagine this. A word of caution: if you do this in your head and it doesn't end up on your paper, the conditions have not been met. Okay? If you just see it in your head, that's great. Make sure it migrates onto your paper. Okay? Okay, so then L'Hopital's rule says that we can then do the exact same limit, except this time we can differentiate the numerator. So the derivative of x would just be a 1. And then the derivative of the denominator, would be what?
1 and 2.
Yes, it's a product rule. So 1 d2 would just be 1 plus 2. d1 would be cosine of x. So now we reapply this limit. The numerator is a 1. So can't we say for certain at this point that L'Hopital's rule will not be applied again? The numerator is 1. It's not a 0 or an infinity, so it's not going to be a L'Hopital's rule again. You try the denominator. What do we end up with? 0 plus 1? Hi. And so your limit ends up being 1. You good? Colin?
Do we need to say the L'Hopital?
Yeah, so you're talking about like this right here?
Yeah.
No, you don't have to say that. But what you do have to say is the 0 over 0 or infinity over infinity. That has to be on your paper. And of course, you can write the thing that says, hey, L'Hopital's rule can be applied. You obviously can write that, no problem. But what you do have to show is that the conditions were met. Okay. So let me come full circle back around to the symbols. If this symbol that I'm circling in purple, if that were an equal sign, do you see the contradiction? In one line, you're saying, hey, the answer to this is 0 over 0, which is like sort of a nonsense answer. You can't divide something by 0 and 0. It's indeterminate, right? And then like half an inch later, you're like, nope, it's equal to 1. What is it? You're contradicting yourself. Which one is it? And so that's why we don't want to misuse the equal sign. If you were to look at a graph or a table, you could see this conclusively visually, right? But just be careful with the equal sign, please. I can't tell you how frustrating it was for me, and I didn't have any of our own papers. Last year at the reading, I would say, oh boy, I'd have to think about this. I bet you I graded, I'm going to say 300 L'Hopital free response questions. 300, I bet. And of those 300, I'm just estimating, of those 300, if I had to guess, I would say 10 of them got full credit.
That's so upsetting.
And almost every single time it was this equal signs issue, or like, hey, equals just means, and my next step was this or that, you know. I was frustrated for the kids, right? Because it's like they got the right answer. They clearly had some idea what they were doing, but they just abused the equal sign. So
Can you do anything or just leave it like that?
they did take that. I like the arrow idea because you're saying I did something to get this. But yeah. Hey, why don't you guys try number 2? I think number 2 would be an excellent one for you guys to do a little practicing with. Lainey.
You don't have to include the L'Hopital's conditions met, right?
Nope. Sometimes people will do this, like they'll write maybe like a little arrow here and just put like a LR or an LH or something, just as a note. Hey, I used L'Hopital's rule. Don't have to do that. We're working on number 2.
No, but like
But it's 0 or 1. Can we do that again?
Oh yeah, you're gonna it's gonna be late.
We're thinking about number 2 right now. Seeing if we can do a little bit of this on our own.
yeah, with it like if you when it did come time to use the equal sign, you just did an arrow with that.
Hey, so some words of caution as we proceed through this. Make sure that we finish solidly. If you do this real quick in your head, I don't think that this is going to take a lot of effort to see what's happening. Basically, you got infinity squared over e to the infinity plus infinity. We are heading towards that other L'Hopital's condition of infinity over infinity. And again, I'm putting an arrow there just saying that this is what, at this stage, I kind of got as I was trying to do this limit. I'm not saying that's the answer, but this is a step in a direction. Make sense? Hey, please don't miss out on details. There's little details here that you might conceivably mess up. And I'd hate for you to not get them because you were unfocused. So this invokes L'Hopital's rule. This is the condition or one of the conditions. And so I'm going to say then I can then try limit as x goes to infinity of the derivative of the top, which is 2x, over the derivative of the denominator, which is e to the x plus 1. Please notice this. There's sometimes a tendency for this thing to come and go and like appear and disappear and sort of like go somewhere else and then reappear. That can't happen. If you have not actually evaluated the limit, it can't go away. It needs to be there the whole time. Because remember, not being there means that you did it, right? Means that I did it in that last step. So we haven't done anything with that yet. So then this, if you try this again, you can probably see pretty quickly that the numerator is 2 times something huge divided by e to something huge plus 1. And so we end up with this infinity over infinity concept again. So this, kind of unlike number 1, the one cycle of L'Hopital's rule didn't get it done for us. It didn't finish it. And so we're going to have to do it again, and we can because we got that indeterminate form again, infinity over infinity. So then what will hopefully be my last step is limit as x goes to infinity. Derivative of the numerator is 2. Derivative of the denominator is now e to the x. And I can say for certain I'm going to be done with this now because the numerator is a 2, right? It's not a 0. It's not an infinity. So I know I'm going to finish here one way or the other. And so as I apply this limit as x goes to infinity, I can now say this, equals, because if the numerator is constant, denominator is getting huge, the answer ends up going to 0. So that'd be your final answer. All right. Questions, thoughts, comments, concerns? Good job keeping up with the double L'Hopital's rule. Seemed like you guys were making some good observations there. Solid? Questions? No? Okay, good. All right, let's take a look at number 3. Love number 3 because number 3 allows us to combine two concepts, at least two concepts, into one. So let's do this one together. Let's just talk it through a little bit. Do this mentally. You don't have to write out all the details here. If you do apply that limit as x goes to 2, and we try this whole direct substitution thing, what happens in the numerator? Right, because it's the integral from 2 to 2. So if you got the integral from 2 to 2, it really doesn't matter what the integrand is. The answer is just going to be 0. So the numerator is 0. And the denominator is negative 2 times 2 plus 4. It's 0, right? And so if you're doing a question like this, you'd say,
It's a T.
oh, doggone it. You know what I did? I misspelled T.
Oh,
Can I,
that would explain it.
I'd like to respell T for you. Or I'd like to respell X for you.
Does that matter though?
Oh, dude, it absolutely matters. A big gust of wind came and blew the T over into the right letter. Now, sorry, yeah, that's a total typo.
Like in
No, hey, listen. Hey, guys, there's a danger here because now I'm hearing people take things way too far. What I did was I misspelled X with a T. That is the only typo. Everything else up there is dead on. Okay? I did misspell that for sure. We need to fix that. But everything else is exactly how it should be. Because if that was a T instead of an X, then it's certainly not a 0 over 0. Because the limit is X goes to 2 does not apply to a T. Right? So, okay. Thank you very much for pointing that out. Top half's totally fine. Yep. Okay. Now that we've respelled correctly, we get this 0 over 0. L'Hopital's rule is in effect. Here's why I like this question. Limit as x goes to 2. Derivative of the denominator is super easy. Just negative 2. Derivative of the numerator, it's d dx of 2, integral from 2 to the x, t squared. What is this? What is it? It's FTC2, isn't it? It's the derivative of an accumulation function. And so if you're differentiating an accumulation function like this, then all you do is you cancel out the derivative and the integral, and you drop the x in wherever you see a t. Technically, we multiply by the derivative of what you dropped in. In this case, it's just going to be a 1. So it'd be the limit as x goes to 2, and the numerator would be x squared minus 4. Denominator is negative 2. Okay. Does that make sense? Nice combination of skills here. So if this is the case, then I'm going to retry my limit. And if I retry the limit based on this L'Hopital's rule concept, what do I get? 0. Yeah. And this is sometimes a little bit uncomfortable because this is 0 over negative 2. And sometimes people would look at this. Can you see why somebody could look at this and be like, oh, that's an indeterminate form. 0 over, and they just sort of forget about the denominator. And they retry L'Hopital's rule again, and they get something totally different. Not good in this case. You just stop right here. 0 divided by negative 2 is just 0. All right. Any questions? Okay, why don't you flip over. We've just got a couple of examples left here. Let's take our time and try to work through these and see how you all do. here is number 4 right there. Okay, let you guys try this a little bit on your own. On number 4. Number 4 is you try to apply the limit as x goes to 0. What was kind of the initial reaction as you applied that limit the first time? Yeah, you should get 0 over 0 for that. Okay, so that of course invokes L'Hopital's rule. That's the condition, or one of the conditions for L'Hopital's rule. So we're going to then do the limit as x goes to 0. And the numerator would be 3x squared minus 12. And the denominator, did you guys remember the chain rule on the denominator? So it'd be 3 cosine of 3x. Okay, so now as you applied the limit again, limit as x goes to 0, what'd you get for the numerator? Yeah, and I'm putting equals here because there's no more L'Hopital's rule. I know that for sure because the numerator is not 0 or infinity. The denominator ended up being 3. Yeah. So negative 12 over 3, of course, is negative 4, and that would be your final answer. So if you got negative 12 for a final answer, that probably means that you forgot to do the chain rule when you did the derivative of sine of 3x. Obviously, easy for you guys to fix that, but hopefully that worked for you. You guys have any questions? You already getting bored with L'Hopital's rule? Too easy? You should pull out the 1 to the infinity thing. You'll be less bored with that. Okay. Yeah. Well, let's do one more. Let's make sure we're good on this last example. So number 5. If you haven't already taken a look at number 5, please do that. Maybe we'll take just another 3-4 minutes here to look at this, and this will be it. So guys, right off the bat, as you evaluated this, I'm guessing that you quickly saw that the denominator is heading towards infinity. Was the numerator similarly easy? It's a little harder to think about natural log of x. I like to think about the graph. The graph of natural log does this. And so as you move to the far right edge of the graph, it is true that it's wanting to flatten out kind of, but it never actually does flatten out. It just continues to increase forever and ever and ever. And so as you go to the far right edge of that graph, the y values will still be increasing without bound. And so we would look at this and say, it's going towards this slowly, for sure, but the limit as x goes to infinity of natural log of x would just be going towards infinity. So this is where you get that L'Hopital's rule condition met, and we would try L'Hopital's rule, so it'd be the limit as x goes towards infinity. The numerator's derivative is 1 over x. The denominator's is 6x. And so we end up with this right here. Might be easiest if we did a little bit of algebra to kind of lead us towards the answer. I kind of like this. Limit as x goes towards infinity. Copy dot flop gives us 1 over 6x squared. Just doing a little bit of algebra in there. Like I said, to me this makes it a little bit more clear. If the numerator is held constant, denominator is getting huge without bound, like this, then the answer is 0 for your final answer. Any questions? Okay, so remember the objectives today were to understand a little bit about indeterminate forms, understand what we can do with them, and apply L'Hopital's rule to these situations. You guys think you're there? Feel like you're on your way at least. Seems like you're doing okay. All right. Well, let's take a look then at